This is January 06 Module 4 and this is question 1a. Define the linear momentum of an object. And this is our answer again that we've had lots of times. Linear momentum is mass times, and again they're looking specifically for the word velocity instead of speed. Using continuous prose, state Newton's second law in terms of the momentum of a body. So this is just the F equals ma, and that's equal to m on v minus u over t. And when you multiply that out, you get mv minus mu, which is change of momentum over time. So that's the rate of change of momentum. And so instead of saying resultant force acting on a body is proportional to its acceleration, we're going to say the resultant force acting on a body is directly proportional to the rate of change of momentum, which is this bit here, over here, and it takes place in the direction of the force. A ball is thrown at a wall so as to strike it at right angles. The ball rebounds from the wall. Figure 1.1 shows how the force on the ball changes with time during its contact with the wall. So there's a graph. It's a force-time graph, and it is the shape of a triangle. And so you can see that the average force on the ball, the force on the ball changes. It goes up to a maximum value in contact with the wall, and then when it starts to move away from the wall, it reduces to a minimum value. So the next part of the question is asking us then, make use of information from figure 1.1. Make use of information from figure 1.1 to calculate the change of momentum of the ball as a result of the collision. And so from figure 1.1, you can see there, if we calculate the area underneath the graph, we are getting the impulse of the ball. We're looking for the change momentum of the ball, which is exactly the same as the impulse of the ball. And so therefore it's the area underneath the graph. Since that's a triangle, then we're calculating half the base, which is 0.4, times the height, which is 8. So you can see the calculation there, half the base by the height, half of 0.4 times 8 gives you 1.6. And therefore the change momentum is 1.6 Newton seconds. Part 2, assume the collision to be elastic. So if we assume the collision to be elastic, we're suggesting that the velocity before it hits a ball is equal to the velocity after it hits the wall. And therefore, I've written that down. If it's an elastic collision, V is equal to U. So since our impulse is area under the graph, and that's given by the change momentum, if, however, U and V are both the same value, then we've got mv minus mv, and that means that the change in momentum is 2 times mv. And if 2 times mv equals 1.6 from our answer up here, then mv, which is the initial momentum, is 1.6 divided by 2, which is 0.8 Newton seconds. Part C. An executive toy, and you'll recognise this as Newton's cradle, consists of 5 identical spheres, each one of mass m. The spheres are suspended by light threads from a fixed horizontal bar so that they are just in contact with each other when undisturbed. Figure 1.2 shows the toy. One of the end spheres is pulled to the side and released, as shown with figure 1.3. The moving sphere makes an elastic collision with the next sphere. Just before the collision, it is moving at a speed of 2u. So I'm just going to write in here 2u in that direction. So as it hits the next sphere, it does, of course, the momentum is passed on, the principle of conservation of momentum, through each sphere, and when we get to the end one, then it moves out. Figure 1.4 and 1.5 show 2 suggestions for what might happen after the collision. Either 2 spheres move out at the end, or 1 sphere moves out at the end. In figure 1.4, both right-hand spheres move to the right with velocity u. In figure 1.5, only the end sphere moves to the right with velocity 2u. Both of these suggestions satisfy the principle of conservation of momentum. Use the equations to confirm that the momentum is conserved in both figure 1.4 and figure 1.5. I'm just going to write in here that the velocity of the first sphere is 2u in both cases. So figure 1.4. Figure 1.4 is the first one there, and you can see that you've got one sphere being pulled to the side. If I just show you up here, one sphere pulled to the side with a velocity of 2u. So the initial momentum is going to be m, which is the velocity, or sorry, the mass of this first sphere multiplied by 2u. And then at the other end here you can see two spheres, each with mass m and each with a velocity of u. So you can see there that I've written down m times 2u, which is your initial velocity of the first sphere, is equal to the two end spheres mu plus mu, which gives you 2mu. And therefore 2mu before and after means momentum is conserved. In the second diagram, you've got your first spheres pulled out with a velocity of 2u. And at the end you've got a sphere, mass m, velocity 2u. And so m times 2u beforehand is equal to m times 2u afterwards. Momentum before and after is 2mu, therefore momentum is also conserved in figure 1.5. In fact, only one of figure 1.4 or 1.5 is physically possible. State which of the figures represents the correct situation and explain why. Now, the way to do that is to have a look, read through the first bit of information, and there's what you need to look at there, an elastic collision. That means the kinetic energy before and afterwards is conserved, and so that's what you have to look at. You have to look at the kinetic energy of this single sphere here and compare it to the kinetic energy of these two spheres here, and do the same here and here. So figure 1.4, you've initially got, if I just show you, I'll just bend this page just to show you. So there's figure 1.4 here, and you can see initially you've got half mv squared, so half m times 2u squared, equal to, so it's the kinetic energy of each one its own, which has got a velocity of u. So it's half mu squared plus half mu squared. Now when you square the 2u, you end up with 4u squared. So that's a half m times 4u squared. When you add these two here, you end up with just mu squared. And you should already see that that isn't correct for our conservation of kinetic energy. 2mu squared is not equal to mu squared. In the second example, however, the one figure 1.5, you've got a half m 2u squared again, all squared, and that's equal to half m 2u squared again. And you can see immediately, without even multiplying that out, that those have to be equal to each other. But just to show you, when you multiply it out, you do again, of course, get 2mu squared equals 2mu squared, and this is the one which is correct. And the reason is collision is elastic, as the kinetic energy before is equal to the kinetic energy after.